Hello and welcome. My name is Anj Gandhi and today I'm going to present my project on logistics and warehouse picking optimization where I have developed a hybrid algorithm combining dynamic programming and greedy approaches to solve one of the most costliest operation in the modern warehouses. So this solution will specifically designed for large-scale warehouses and distribution centers like those operated by Aldi, where order picking accounts for over half of the operational costs. So let's dive in and see how we can optimize this critical process. So moving on to the next slide, here is the agenda. Here's what we will cover in the next few minutes. First, I will introduce with the problem and explain why this matters for companies like Aldi. Then we will review existing solutions in the literature, then identify limitations and examine proposed hybrid approach. Finally, I'll walk you through the system architecture, algorithm design, and expected benefits before concluding with the development timeline. So here is the introduction. So let me start by defining the core problem we are solving. In a typical warehouse, when multiple orders arrive, each are containing items scattered across different regions, or I can say as locations, because must collect all these items efficiently. The challenge is determining the optimal route and sequence to minimal travel distance, time, and ultimately the cost. Why does this matter? The number of staggering order picking represents the 55% of total warehouse operational cost, with e-commerce growing by 65% since 2020. This problem has become even more critical for a company like Aldi operating multiple distribution centers across the UK, optimizing this process, which would save over 10 million pounds annually. So the key challenge is include the dynamic order arrivals throughout the day, multiple warehouse zones with different temperature requirements for fresh, frozen, ambient products, and the peak demand periods, and most importantly, the worker safety and fatigue concerns. So, moving on to the next slide, this is the literature review. So now we are examining the already existing the research literatures. So warehouse picking is fundamentally a variant of famous traveling salesman problem combined with the bin packing and route constraints. So making NP hard in computational complexity. So I reviewed four classical algorithms. The nearest neighbor greedy approach is the simple with O(n) squared complexity, but only achieves 70 to 80% efficiency because it's myopic. It can't see bigger picture. Genetic algorithms perform much better, 90 to 95% efficiency, but are too slow in real-time optimization. Simulated annealing achieves 85 to 92% efficiency, but has prohibitively long run times. The Bellman help card dynamically programming algorithm is theoretically optimal at 100% efficiency, but its exponential complexity of O(n) squared to the n makes it practical only for the very small problems, fewer than 20 to 25 items. So, moving on to the next slide, this is the proposed solution. So my core, so this is, so this is the proposed solution. So my core innovation is to combine dynamic programming for optimal decisions, with greedy algorithms for efficiently global construction. So the system has three component. Component one is the order cluster module, which uses greedy approach to group items by warehouse zones and proximity. So this is crucial because it reduces the problem from O(n) individual items to OK clusters where K is much smaller than N. And component 2 is the DP route optimizer. Within each cluster, I apply the Bellman-Held card uh, algorithm to find the optimal picking sequence because all clusters are small, typically 10 items or fewer, exponential complexity becoming manageable. So component 3 is the intercluster router. uh, the greedy router, which determines the optimal sequence for visiting clusters using enhanced greedy sequence with uh, the look ahead heuristics to avoid obviously poor decisions. The result is near optimal solution with practical computational efficiency suitable for real-time deployment. Moving on to the next slide, we have the block diagram. Here's how the data flows through the system. So order enters through the warehouse management system. The clustering module groups items efficiently. Each cluster is then optimized during the dynamic programming. The internal cluster router determines the visiting sequence, and finally we output an optimized picking route. So the entire process completes in under 2 seconds for typical warehouse scenarios with 100 or more items. So moving on to this is the pseudo code using the greedy approach. So there are three phases, and uh, moving on to the next slide, we have the expected benefits. So the performance and improvements, what we can expect is like 25 to 35 reduction in travel distance compared to the methods. So 30 to 40% faster order fulfillment, completion under 2 seconds for batches of 100 plus items, solution quality at 92 to 97% of theoretical optimal linear scalability as warehouse size increases, and the ability to reallocate routes in the real time as new orders arrive dynamically. And this is my 10-week implementation schedule. Weeks 1 to 3 focus on. So uh, this is my 10-week implementation schedule. So week 1 to 3 focus on algorithm implementation, developing the cluster module DP solver and greedy router with comprehensive testing. Week 4 and 5 building the simulation environment with virtual warehouse models and realistic test data sets. And in the week 6 and 7, involve the extensive testing, performance comparison against baselines and parameter tuning. And week 8 and 9 cover the integration with the warehouse management system and pilot testing with real operational data. Week 10 completes the documentation and the final project. Uh, So here I conclude my presentation. So the current project is in the started the implementation stage, and the project presents a practical implementable solution to the warehouse picking optimization that balances theoretical optimality with computational feasibility. So the key achievements are near optimal solutions at 92 to 97% efficiency, real-time performance under 2 seconds, scalability to large warehouses over 10 million in potential cost savings for all these network, and improved worker safety through reduced physical strain. This hybrid approach demonstrates that sophisticated algorithms thinking can yield substantial operational improvements when carefully designed to address real-world constraints. So this was the conclusion. So here are the references which were used in the literature review. And I thank you for watching this presentation. Here my presentation ends.